Hello and welcome to Module 4, Modeling and Simulation. In this model, we'll talk about simulation by hand. Consider again the simple processing system we discussed in our introductory overview. In this case here, we have a single server, which is system, with one drill press machine. You can see there are parts arriving, parts waiting in queue, a machine, in this case a server, and then finished parts. In our single server system, there are only two possible events that can affect the state of the system: the entry of a part into the system, or an arrival, and the completion of a service or drilling on a part, or a departure event. The arrival event occurs when a part or entity enters the system. The flow diagram for the arrival event is listed below. As it comes in, there's a decision made whether the server is busy. If the server is busy, then the unit enters queue and then waits until the server is no longer busy. If it is not busy, then the unit can enter service immediately. Incorporating this logic will show that as the system progresses and more data comes through, the system will be able to respond and you'll be able to see the true impact of the queuing. If a part or entity has just completed the service, the simulation event will precede the departure in a similar method. In this case, the event determines if there's a unit waiting. If there is not a unit waiting, it will remove the waiting unit from the queue and begin servicing the unit. If there is a unit waiting, it will begin the server idle time. Again, note that the server only has two possible states, busy or idle. This is a very simple model for our illustrative purposes, and in actuality, most models will be much more complicated. So in simulating a queuing system, you must determine how the events we just described can occur in simulated time. That's where the event list comes into place. This tracks the future times at which the different types of events can occur. The simulation clock will time for arrivals and departures are computed with a simulation table, and we can compute these clock times by hand, which we will call hand simulation. Before we go into simulating by hand, let's talk through some definitions. First, if three parts arrive at our drill press at the following arrival times, 0, 6.84, and 9.24, the inner arrival times will be listed as 6.84 and 2.0. The 2.0 is the difference between 9.24 and 6.84 and shows how much time that had to wait from the second one until the third one. In a grocery store hand simulation, consider a small store that only has one checkout counter. The problem would be to analyze the system by simulating the arrival and service of 6 different customers. The inner arrival times will of course be random because the customers can come whenever the customers are ready. So we will assume that these times are random and generated from 1 to 6 minutes apart. You can see in the table that is listed below. The inner arrival time is the difference between when they arrive compared to the first one, as opposed to the arrival time on the clock, which is the real time when they arrive on a calendar basis. The first customer, of course, has the same inter-arrival time as on the clock because there's nobody waiting ahead of him or her. The second customer has a 2 for arrival time on the clock and a 2 inter-arrival time. The third one has a 6 and a 4. The inter-arrival time the arrival time on the clock starts with a 6. However, the 4 inter-arrival time is 6 minus 2, which is the previous customer's arrival. You can continue this on through the remainder of the table. Service times are generated assuming that these times were generated at random from a distribution of service times. Again, in the case of a grocery store chain, we will assume that the time in order to process the checkout for the customers is random. This case here lists the service times that it takes to process each of the respective 6 customers. So now the table on the next slide is the simulation table for the grocery store example that we will be filling out, and we'll walk you through this step by step. Since we know the service and inter-arrival times, in theory we could fill these columns out as a priority. In this case we won't, because this is a very simplified model and the intent is to walk you through and show how this hand simulation works. Starting with the blank chart, you see the customer 1 through 6 in the first column, and then you have columns for time since last arrival, arrival time, service time service begins, time customer waits in queue, the time the service ends, and the time customer spends in the system, and then the idle time of the server. At time 0, the first customer arrives. In their case, the service time was 2. So the customer starts at time 0, and after 2 service time, regardless of what units it is, that's when the customer is complete. We then fill that first line out with all the relevant information. the time since last arrival would be not applicable for the first customer, and the arrival time would be 0. Since the service time was 2, the time began at service 0. There were no customers waiting in queue because the customer in the first case here could be serviced immediately, so that time is also 0. The service ends at 2, and then the time customer spends in the system is 2, and then the idle time of the server remains at 0. At time 2, the second customer arrives, customer number 2. Their inter-arrival time was 2 and had a service time of 1 unit. That's expressed as this graph on the x-axis right after service time 1. You can see that there was no idle time between time 1 and 2, and there was also no wait time for unit 2. We then fill that out. Time since last arrival is 2, since that's when they arrival right before it came through. You can see that from the previous line. The arrival time would then be 2, the service time would be 1, and the service time could begin at time 2. The customer had no time to wait in queue. The service time therefore ended at 3 because there was no time to wait in queue. It began at service 2, and in 1 service time, the end would be, of course, 3. The customer then spent the total amount of time in the system was 1, and again, there was no idle time for the server. At time 6, the third customer arrives. In this case here, the third customer had a service time of 3. Note that unlike the first 2 steps, there is a wait-in time between service to customer 2 and customer 3. You can see there's a gap of 3, which means that's how long that the server had to wait for the next customer. So the time since last arrival is 4, and then the arrival time is 6. The service time would then be 3, which is how long that service for the third customer takes. The time began at service 6, the customer did not have to wait, and the time was able to end at time 9. The customer spent 3 in the system, however, the server did also incur 3 of a wait time. At time 7, the fourth customer arrives with a service time of 2. Again, unlike the previous times, the customer came in and there was somebody else already in queue, so the customer, even though they had a service time of 2, they could not begin until the third customer was completed. Therefore, while they arrived at time 7, they could not begin until time 9. The time since last arrival is 1, since they arrived at 7 and the previous customer arrived at 6. The service time was 2, but the service time began at time 9 since the customer had to wait in line for 2 units. The service time ended at 11 because the service time started at 9 and took 2 to service them, and then the customer eventually spent 4 of the 4 units in the system. So even though they actually had 4 units in there, the 2 units were service time and 2 units were wait. However, in this case here, the server was continuously working, so there was no idle time. At time 9, the customer number 5 arrives. Similar to the previous customer, they arrived right when the fourth customer was going. So they had to wait until customer number 4 was completed. So while they were there at time 9, they could not begin until time 11. Since the previous customer arrived at time 7 and they arrived at time 9, the time since last arrival is 2. The service time was only 1, and service time could not begin until time 11. That way, the customer waited for 2 units and then ended their service at time 12. Ultimately, the customer spent 3 time units in the system, and again, the idle time was 0 for the server. The last customer number 6, came in at time 15. Note that in this case, the customer came and there was nobody waiting in line ahead of him or her. However, the server had to wait idle from when customer 5 left until customer 6 arrived. The time since last arrival would be 6, since they came at 15 and the prior customer arrived at 9. The service time was 4, and the service was able to begin at time 15, right when the customer arrived. Since there was no waiting queue time, and the service time was 4, the time ended at 19. The customer spent 4 in the system, and then the server was idle for 3. Now that we've completed our table, we can report the findings about the system and measure the system's performance. A couple things to point out. First, the time since last arrival column is identical to the ordered inter-arrival times given in the column. That is something that, again, you can create and fill out right at the very beginning of the system. However, I would still advise you not to do that and take the system through line by line. The service column is identical to the ordered service times given in the problem. Those 2 things will always be the case and are a good validation check once you're done once you're done with the hand simulation to verify that you have done the simulation correctly. Now, in completing all these, you can total up the different columns. The total amount of service time, column D, is 13 units. You can also total the amount of time that the customer waited in queue, or is time F, which is 4. And lastly, we will total the last two columns, which are the amount of time the customer spent in the system, which is 17, and the overall idle time of the server, time 6. Note how they also relate to each other. For example, the time the customer spends in the system is 17 should be the sum of the service time and the time that the customer waits in queue, 13 plus 4, which it is in this case. The average waiting time can be computed by using the totals that we just calculated. For example, you can take the time the customer waits in queue, 4, and divide by the total number of customers, 6, and get the average waiting time, which is 0.67. While this is an average, remember that averages can be misleading because some customers had to wait long times and some customers did not have any wait time at all. The probability that a customer had to wait in queue is simply the number of customers who waited divided by the number of customers, or 2 divided by 6, or 0.33. This is good information to show, given that the average could be a little bit misleading. The fraction of idle time of the server can be computed by the total idle time of the server divided by the total runtime of the simulation. In this case here, that is the total of column I and the last number of column G, which represents the time the service ends. Therefore, 6 divided by 19, or 0.316, is the fraction of idle time of the server. Average service time is the total service time divided by the total number of customers. In this case, that is the total of column D, or 13, divided by the total number of customers served, 6, or 2.17. The average time between arrivals is the sum of all time between arrivals divided by the number of customer arrivals minus 1. The reason that the number of customer arrivals minus 1 is because we have 6 customers, however we only had 5 waiting times between customers since the first customer didn't have any waiting before him or her. In this case here, you would calculate this by taking the total from column B and dividing it by the number of customers, 6 minus 1, or 15 divided by 5 equaling 3. The average waiting time of those customers who had to wait would be the total time customers waited in queue divided by the total number of customers who waited. The total of column F is the total time of customers waiting in queue, and you can tell from the table before that the total number of customers who had to wait were only 2. Therefore, 4 divided by 2 would be 2. The average time a customer spends in the system is calculated by the total time the customer spent in the system divided by the total number of customers. You can get this by getting total from column H, dividing it by the total of customers of 6. 17 divided by 6 equal 2.83 units. Looking at these, a decision maker would be interested in the results as we have just calculated them. However, there are some caveats that would have to be included. First of all, this is an extremely short run. We only simulated 19 minutes of the grocery store and just 6 customers. This clearly is a very short-sighted representation and does not truly reflect how the actual system will perform over a much longer duration. It also doesn't have any replications since it only has one sample size. Again, multiple replications doing this test over and over will get more data and get more confidence within our system. Also, it will allow for us to understand different behaviors such as shopping patterns, as customer arrival times may vary or depending on the day. Conversely, the server or processing times may also vary depending on the type of labor or the staffing that they have based on those customer arrival times or based on the time of day.